Bismillah, alhamdulillah, wassalatu wassalamu ala rasulillah. Inshallah, in this lecture, I will go with you over section 7.5, which is about a general guideline for integration. It is a strategy how to integrate functions. So it is like a summary for sections 7.1, 2, 3, 4 together. Of course, the first thing that you need to know when you want to integrate is the table of basic integration formulas. Is it direct integral or not? So first of all, you should be aware about this table or about these 20 integrals. And of course, you can add more. Every one of you should has his own table. So first of all, if you want to integrate, you should. I think the first thing that you should always do is to simplify. So try to simplify your integrand as much as possible. So for example, here, before doing anything, you can just multiply. So when you multiply, you will have a sum of two functions. Each one of them is easy to be integrated. When you have trigonometric functions, try to write tan in terms of sine and cosine. Or you can write sine secant in terms of tan. You can do whatever you do. But what is important is that the new integral that you will have is easier than the first one, simpler than the one that you started with. Like here, when you write tan as sine over cosine, you will have a cancellation here. You will have sine cosine, and you of course use the u substitution. You can put this equals to u, and this will be du. This is one way. Or you can use also another identity, which is the double angle identity, and this integral at the end will be, of course, negative cosine 2 theta over 2 plus c. So it is up to you. You can also use this u squared over 2. Here, for example, sine x plus cosine x, you can expand, then use the Pythagorean identity. That both of these will be 1. And here you can do the same. You can write this one as sine 2x, or you can consider this as u, and this will be du with negative, of course. This will be negative du, this will be negative. No, when you put u equals to sine, of course, du is cosine. So it is just du. So as I said, the first one is to simplify. Try always to simplify as much as possible. If the simplification doesn't help, you can look for an obvious substitution. And of course, remember that when you think about a substitution or a u substitution, you are thinking about a function, and its derivative also, its differential, it is also occurs inside the integral. So you have both. You have the function and you have its derivative inside the integral. Otherwise, you cannot use this, because this is coming from the substitution rule. If you have a function of another function, then multiplied by the derivative of the inner function, then you can use the u substitution. Otherwise, it has no meaning. You cannot use it. So this is the idea. This is u, and what is here is du. So like here, for example, you can use 7.4, by the way. You can use here partial fractions, but it is easier to use u substitution, because if you think about this to be u, then this will be du just by a half. If you just multiply by 2 and divide by 2, then you will have a function in the denominator. You will have here a function, and here you have the derivative. And in this case, just it will be the ln of the function in the denominator. So this one, it is just, this integral is just the half of ln the absolute value of x squared minus 1 plus a constant. Because you have x there. Without x, of course, you need to apply the partial by fractions, by partial fractions. So step or strategy number 3 is try to classify your integrand according to its form. So what is it? Ask yourself, what is the function inside the integral? Is it a trigonometric function? So if you have trigonometric functions and you have a product of them, then if you have a product of sine or cosine, tan, secant, cotan, cosecant, then think about section 7.2. how to use the techniques. It depends on the power. Are they odd, even, and so on. So you should think about the trigonometric integrals. If the function inside the integral is rational function, polynomial over a polynomial, so you need to think about partial fractions, section 7.1. If your function is a product of powers of x, is x to the power n multiplied by exponential or trigonometric function or logarithmic function or whatever, then you can think about integration by parts, 7.1. You need just to choose what is u, what is dv, and according to the advices that you learned in that section. Finally, if you have, when you are classifying what you have inside the integral, ask yourself, do you have radicals? طبعا, it is easy if you classify what is the kind of your radical is. So according to the kind of radical that you have, you can choose the right substitution. For example, if your radical is this way, it is x squared plus a squared, or x squared minus a squared, or a squared minus x squared. If it is of this type, it is of course advisable to think about trigonometric substitutions if the your substitution doesn't work. Another type of radicals that you may have when you have the integrand, when you have the radicand, when the radicand is linear, not a radical of a quadratic of this type. So when you have a linear to the power n, whatever here, it could be square root, cubic root, and so on. So rationalizing substitutions that we have learned in 7.4 works here. So just both u equals to the radical. And this will rationalize it. It will convert it to a rational function. So if all of these three steps, the previous three steps, doesn't work, try again. How you try to think in a different way now. So what you need to do, always just remember that basically we have, of course, many techniques for integrations, but basically we have two methods of integrations: by parts, which is 7.1, or substitution. It could be u substitution, trigonometric substitution, the rationalizing substitution, and so on. So try substitution and think about different substitutions. Here you have, of course, you have to be smart here when you substitute. And of course, you may find a substitution that is more effective than others. It is sometimes not only one substitution works, maybe more than one substitution. So here it is your of course your time to think about what is the good substitution that can make it much easier. Also, don't forget to try integration by parts. When you look at the integral and the substitution doesn't work, think about by parts, integration by parts, especially if you have inverse trigonometric functions or logarithmic functions inside your integrand. Manipulate your integrand. Of course, try to play with your integral. Perhaps you may multiply by the conjugate, you may rationalize the denominator, you may use trigonometric identities. Use all the algebraic tricks that you have before, multiplying by a number, dividing by the same number, adding the number and subtracting the same number, adding a 0 or multiplying by 1, and you know, all the algebraic manipulations that you have learned. For instance, here you can use the substitution, of course, that you learned in section 7.4, but of course it is easier here to multiply by the conjugate of the denominator. So and then use the trigonometric identities. This is what you could have. And after the simplification, this is a direct integral, and of course this is just, you can use the substitution here, u substitution. Then, of course, you need to relate your problem. If all of what we have done before doesn't work, try to relate the problem to previous problems. طبعا this will come يا شباب when you build up some experience in integration. You may use integrals that you have already found before. For example, he provided here a good example. If you want to find this integral, tan squared x secant x tan x, this is not an easy integral, by the way. If you look at it, it looks cute, but it is not that one. It is in fact a challenging integral. We did it, we solved it. Just check section, I think 7 point, I'm not sure, but 7.2 and 7.3. We have solved it there. Here, what you need to do, of course, you will just make tan squared secant squared x minus 1. Then you will have two integrals. One of them is secant to the power 3, and this integral we have shown this integral in 7.2. So this integral is already done. We know we will use here, of course, integration by parts. So we have solved this one in 7.2, example number 8. So now, when you evaluate this integral, use your previous experience, use previous problems to solve this one. So it will be just an additional integral that the integral that you have before. Use several methods, and this is of course the last solution. Sometimes you need one method, it is not enough. You may need to use substitution, then integration by parts, or integration by parts, then substitution. So it depends on your integral. You may use several methods. Let me summarize the strategy of integration for you. So simplify as much as possible. Try to find a clear substitution and that make the integral much simpler. And classify your integrand according to what is it? Is it trigonometric or rational or by parts or radical? Try again, try substitution, try by parts, try to simplify algebraically your integrand, relate your problem to previous problems, use several methods or several substitutions. Let's take an example here. Now, first of all, you should ask yourself, is it direct? Can I do it directly? Can I know what is the antiderivative? Can I use the basic table or not? Then think about what do you have here. If you look, we have here trigonometric functions. So it is natural here to think you have tan and cosine. None of them is the derivative of the another one. So thinking about your substitution here is not practical. But if you think about writing tan as or 1 over cosine, 1 over cosine to the power 3. If you think about it like secant to the power 3, you will have integral like this, and you know how to do this. This is 7.2. What you will do, you will just take a power from here, and you will have secant tan. I think this is what he did exactly here. No, he didn't. Let me do it for you. So this will be equals to the integral of what? Tan squared x secant squared x. And here you will save a factor of secant and tan. Then this will be your du. This is my du. So now, according to that, u will be secant x. So I need to write tan, this tan, in terms of secant. So this will be equals to the integral of secant squared x minus 1, secant squared x, and here you have secant x tan x dx. So this is going to be u squared minus 1 multiplied by u squared, and here you have du. And of course, it can be integrated after that simply. An alternative way is, as I said at the beginning, the alternative way is to write tan in terms of sine and cosine. Then you will have sine to the power 3 over cosine to the power 6, and you will do the same. You will save a factor here of sine, so it will be sine squared x sine x dx, and this will be your du. And what you have here, it is cosine, and here cosine. So because sine x is du, of course, u is going to be cosine or negative cosine. So you will write here, this is cosine to the power 6, you will keep it as it is. Then you will write sine squared as 1 minus cosine squared x, all to the power 1, because it is just sine squared. This is all over cosine to the power 6x sine x dx. Now, if you put u equals to cosine, then this is going to be 1 minus u squared over u to the power 6, and this is just negative du, because if u is cosine, du is negative cosine. And of course, it can be now easily integrated. Here it is. This is exactly what we mentioned there. So you can, of course, make it u squared minus 1 to get rid of this negative. So this is exactly this one. And of course, write it as a power function and integrate it after that. Another example here is about an exponential function. But of course, it is not the direct one that we know. This is e to the power x dx. This is clearly e to the power x plus c. طبعا, if you have the integral of x squared dx, let's say, let's start with this one. When you have this integral, or much easier, this integral, here you have, this is just the integral of e to the power x squared multiplied by 2x dx. And this will be e to the power u du, and which will be e to the power u, because if this is u, this will be du. So easy. And of course, one of the integral that we cannot find, I will mention this at the end. This one you cannot find its integral, by the way. You cannot find an elementary function equals to this integral. I will explain this at the end of this lecture. But here, with this integral, we can do something about it. So what we could do here, we don't have more options, of course. One thing that you can try to do is to use substitution, to use the u substitution. So it is not bad to think about putting u equals to square root of x. In this case, what you will have u squared equals to x, which implies that 2u du equals to dx. And in this case, you will come to your integral. It will be e to the power u, and this dx will be 2u du. If you look at this integral, you will realize that this is a product of power function and the exponential function. And in this case, you can use integration by parts. So you can solve it by parts. Just use by parts. You will put, but it is not good to use, if you are going to use integration by parts, it is better to use t instead of u. So this will be t. I think it is much better to do it from the beginning. So this is t. This is t, and this is the integral of t dt. It is the same, of course. Now you will put u equals to t and dv equals to e to the power t. Then du will be dt, and v will be the exponential of t. And of course, uv minus v du, and you will be able to integrate it. So here we use two methods, substitution and then integration by parts. Here it is clear, Shabab, that this is a rational function. So, and the degree of the denominator is greater than the degree of the denominator. So we will start by long division, then integration by parts. This is 7.4. Okay, this is a good one. Also, we have here a combination of logarithmic function and good. It is about len here, but inside the square root. So we have a function of len. What is this function? It is the square root. So it is natural here to think about putting u equals to len x. But of course, it is important to ask yourself, do I have the derivative of len x inside this integral? If you put u equals to len x, the derivative, it is 1 over x dx. And we have it. Look, this is dx over x. Here it is. So it is going to be u du, and this is square root of u. It is just u to the power negative half du. And now it will be integrated as a power function. This is an integral also. Now, according to the classification of the integrand function, what we have here? We have a radical. So it is natural, I think, to think about rationalizing substitutions. When you have a radical here, you can think about this one. It works, by the way. I think it works, but I'm afraid that it will be a little bit long. Try to do it, practice, and do this substitution. Of course, u squared will be 1 minus x over 1 plus x. The problem here, when you differentiate, you will have 2u du equals to the derivative of this one. You need to differentiate to apply the quotient rule here and then dx. But there is an easier way to do this. What is it? Is to distribute, as we said, manipulate your integral. So this is 1 minus x squared, 1 plus x dx, and you can multiply by the conjugate over here. or by one of them, one of the radicals. So it is for example, here he multiplied, I think, by the radical of square root of 1 minus x squared to just make the numerator, of course, without radical. So he just multiply by this radical, and of course after that you will have an integral like this. Here you have to separate, I think, the integral. Yes. Now here we have square root of 1 minus x over 1 plus square root of x. We did it. When we multiply this by this, we will have the radical gone, and we have 1 minus x, and this is the square root of 1 minus x squared. Now, of course, you can write this integral into two integrals. So this will be 1 over square root of 1 minus x squared minus the integral of x over square root of 1 minus x squared dx. For this integral, I think it is clearly sine inverse x. You know that it is from the table of basic integrals. And here, indeed, it is about an integral like this. It is the integral of 1 minus x squared all to the power negative half multiplied by x dx. So it is just about the derivative here. You need to provide the derivative, which is negative half, negative 2. So you will divide by 2 and multiply by 2. And you will have, of course, your integral after that will be negative half multiplied by 1 minus x squared all to the power negative half divided by a half. And of course, you have provided the derivative, it will be plus, because here the derivative is negative 2. Here it is. This is what is it going to be at the end. So look, we have started with an almost a new integral that we didn't see before. But what we did, we tried to just manipulate the integrand function. As I said, you can also use this substitution. It works, by the way. Just try it. Now, I think we are ready now to ask ourselves this question. We are almost done. Now, can we integrate all continuous functions? So whatever you will give me here, I can find the integral. I can find if whatever the function that you will give me here, I can find the antiderivative of this function or not. So for derivatives, it is clear we can differentiate any function. But what about integral? For example, can we use it to integrate this? This is what I said for you before. This is one of the functions that when you integrate it, there is no elementary function equals to this integral. So the antiderivative, if this is f, its antiderivative is not an elementary function. What is the function? What is the function? Think about a function. If you differentiate, you will get e to the power x squared. It is not an elementary function that we know. Of course, it is written. It is a higher level function that is not algebraic or transcendental function that we know in this course. So the answer is no. Can we use it to evaluate this? All of these techniques that we have done before, can we use it to evaluate this? The answer is no. At least not in terms of functions that we are familiar with. So to understand this much better, why we don't have indefinite integrals for some continuous functions, if the functions that have been dealt with in this textbook are called elementary functions. What we mean by elementary functions is polynomial, rational, power functions, exponential, logarithmic, trigonometric, inverse trigonometric, hyperbolic, and so on. All of these functions, of course, are elementary functions, or any algebraic combination of them. So if you add, multiply, divide these functions together, you have what is called, for example, this one. It is a combination of radical, rational, logarithmic, hyperbolic, exponential, trigonometric, combination of all of these, and it's still elementary function. It is an elementary function. So if f is elementary function, then its derivative is elementary function. This is a fact. Because if you differentiate a function of all of previous types, you will get a function from that type or another type. Whatever you will get, the derivative is still elementary function. It is still trigonometric, exponential, rational, and so on. But but the integral is not. So if you have a function that is elementary, then its integral is not necessarily an elementary function. And we can consider this just an example, as I told you before. If you want to integrate this, طبعا this function, if you want to find the indefinite integral for it, it is not an elementary function. This integral is not an elementary function. If you think about it as a function, so if you change the variable just in a matter to understand what we are talking about. So if you think about this function, it is now a function of x. This should remind you about section 5.2 or 5.3 about the fundamental theorem of calculus. So now this function is continuous by the fundamental theorem of calculus, and its derivative, if you differentiate this function, you will have e to the power x squared. So you have this is elementary function, its derivative is elementary function. Now, because it is continuous, of course, this integral exists. Now, this function has an antiderivative, but it has been proved that this antiderivative is not elementary function. Not in this textbook, of course, it is proved somewhere else. This means that no matter how hard we try, we will never ever succeed to evaluate this integral in terms of functions that we know. And this is not only for this, by the way. You can approximate this integral. We will do that, inshallah, in chapter 11. We will write this function as infinite series, and then we can approximate its integral as a summation of power series. But for now, what we will say about such integral, that it is not an elementary function. This is also the same can be applied. The same thing can be said about these integrals. Do not try to find a function or elementary function that equals to these integrals. This is easy, just sine x over x. You cannot integrate this function. You cannot find an elementary function that equals to this integral. The same when you have 1 over ln x. This one, just look at it. When you have x to the power 3, it is not easy to find this integral in terms of elementary function. And you can, of course, generalize this idea to many functions of this type. But of course, the majority of the functions that we have, the majority of elementary functions don't have elementary antiderivatives. But of course, yes, when we give you in the quizzes or in the exam, in this textbook, most of the integrals that we will give you are integrals that can be represented in terms of elementary functions. So don't just, when you find an integral that is not easy to be found, don't say that it is not an elementary antiderivative. No, this is just, I'm telling you this because to be aware about that. We cannot integrate all the functions, or we cannot find all the indefinite integrals in terms of elementary functions. These are the suggested problems that for you to practice and solve. And I have added in the slides of this section all the exercises of the textbook, almost all. I'm not sure about that, but they are like more than 80 exercises. So this is just for you if you want to practice more and more and challenge yourself and see that how many integrals that can you find. And all of these, by the way, can be found in terms of elementary functions. Yes, and also some old exam questions, they are here and they are added with a complete solution. Thank you, Shabab, and see you inshallah on Sunday. Please prepare for the next class. It is going to be a flipped class. We will practice on the class of Sunday. Thank you and see you then.